Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our discussion about Taylor and Maclaurin series, and we're going to kind of wrap it on up with one last topic, and this topic is going to be a review of your binomial theorem that you probably learned in your pre-calculus or college algebra course, or at least you should have learned in your pre-calculus or college algebra course. And the way I'm going to derive it here is I'm going to use calculus, but it'll go full circle back to your college algebra. So one thing we know so far is that if there is a Taylor series expansion, or better yet, a Maclaurin series expansion for this function, and if they're equal to one another, then it would be of the form summation n equals 0 to infinity, the nth derivative of f, this function being f, that is, evaluated at 0, because we're talking about the Maclaurin series, divided by n factorial, and then x to the n. But our job here is to find out what all of those coefficients that these guys right here, what they are. So let's go ahead and list out the function. First of all, f of x, right, is equal to quantity 1 plus x to the kth power, and then a few of its derivatives until we find a pattern. So f prime of x is equal to k times 1 plus x to the k minus 1. F double prime of x is equal to k times k minus 1 times 1 plus x to the k minus 2. And so on and so forth. I'll just probably go to maybe 4 derivatives. So k times k minus 1 times k minus 2 times 1 plus x to the k minus 3. And like I said, I'll just go, actually maybe in general, I'll just say dot, dot, dot. Now let's kind of find a pattern here for the nth derivative. You could see that if we take the first derivative, or better yet, the second derivative, you could see that let me highlight this, the second derivative is right here, but we stop this reduction, this step down from k to k minus 1 to whatever, we stop at 1 above the derivative. So if it was the third derivative, we're stopping at 2. If it was the 14th derivative, we'd stop at 13, and so on and so forth. Also, note the second derivative has a k minus 2, third derivative has a k minus 3, and so that kind of indicates the pattern that I'm looking for. The nth derivative of f with respect to x is going to be k times k minus 1 times k minus 2 all the way down the line, dot, 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 until you get to k minus, and then one more than n. That is, we've lost n, just like in this case right here, we've lost 3, but then we've added back 1. Okay, and then of course this would be 1 plus x to the k minus nth power. Okay, so that gives me what the nth derivative looks like. So let's go ahead and find out what these look like at 0, specifically the last one. So I'm going to write that down below. This is the nth derivative evaluated at 0, and if you plug 0 in, you just have 1 to the k minus nth power times this weird looking product, right? K times k minus 1 times k minus 2 all the way down the line to k minus n plus 1. All right, so that tells me what the form is for that numerator. So I'll go ahead and insert that in here. It's just going to equal the summation from n equals 0 to infinity. Now there's something wrong with what I'm about to write. So let me just say that first. There is something wrong here, and we're going to discuss it, because this is actually, maybe I shouldn't write it then. I'm going to write it down below and we'll talk about it. Because this is actually what most authors will put in books. They'll say, oh, this is the same thing as n going from 0 to infinity, and we see the nth derivative at 0 is k times k minus 1, yada, yada, yada. So k times k minus 1 times k minus 2, all the way down the line, dot, 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 until you get to k minus n plus 1. And this is all over n factorial x to the n. And that's what they write in the textbooks, but there's something slightly, or actually pretty terribly, incorrect about this. The reason why I say this is because if you expand this, when n is equal to 0, you have this. Okay, I'm going to start at k, and I'll go down to k minus 1, and I'll decrease and decrease and decrease, getting all the way down to, again, we're at 0, right? Down to k plus 1. Do you see an issue with that? All over 0 factorial, x to the 0th plus ... There is an issue there. You're saying start at k and decrease until you get to something greater than k. That can't happen. Not for n equals 0. Now, n equals 1, it actually does work. So n equals 1, let me erase that dot. N equals 1 looks like this, k, and then you're going to go all the way down to k minus 1 plus 1, which is just k actually, so I can just stop at k itself. So you're going to start this decreasing pattern until you get all the way down to k minus 1 plus 1, or just k, all over 1 factorial, x to the first. And so that is okay. That actually works out. And so there's nothing terribly wrong with that. And it is actually true. But the very first one, the mathematics is just broken. And I have yet to see anybody correct that. And it's kind of annoying to me. So the reason why it's broken is because we're actually looking at the pattern for the derivatives, right? So notice the derivative has a k, and then a k times k minus 1, and a k times a k minus 1 times a k minus 2. But not the function, not the 0th derivative, right? So what we can do to adjust for this poor notation, I think, is to run this power series once. So in other words, let n equal 0, and you'll just get f of 0 divided by 0 factorial times x to the 0th plus, move that down a little bit, a summation starting at 1 going to infinity of this notation here, k times k minus 1 times ... down the line to k minus n plus 1, all over n factorial x to the n. That would save so much frustration from the student's standpoint. Okay, all I need to do here is find out what f of 0 is, but f of 0, if you could see this circled piece right there, plug in 0, it's 1. So this is actually 1 plus the summation n equals 1 to infinity of k times k minus 1 all the way down the line, ... to k minus n plus 1. And trust me, it'll save you just a ton of frustration if you remember this formula more than the formula you might see in your textbook. However, your author might also give an alternate formula. So let's go ahead. I'm going to scroll down a little bit to make room here, but let's go ahead and talk about what the alternate formula is. Now remember, the nth spot looked like this. K times k minus 1 times k minus 2 all the way down the line to k minus n plus 1 over n factorial. That's what the nth term of that expansion was. But let's go ahead and remind ourselves of an old notation, a very old notation you might remember from your college algebra days. This notation, it's called choose notation, and that stands for k choose n. It is actually the number of ways you can choose n objects from k. In other words, if you have 10 cars, how many ways can I choose 2 of them? Well, I could choose the first and the second, or the first and the third, or the first and the fourth, or the first and the fifth, or the second and the eighth, or the third and the ninth, right? There's all different ways you can choose 2 cars from 10. So turns out that mathematically, and you should have learned this way back when, that this is going to be 10 factorial. Let's just work with this because I think it's easier to see. 10 factorial over 2 factorial times 10 minus 2 factorial. And if you do some cleanup here, you'll get that this is the same thing as 10 factorial over 2 factorial times 8 factorial. Now I chose a very large expansion, so this is kind of shame on me here, but I'll go ahead and do it. This is the same thing as 10 times 9 times 8 factorial over 2 factorial times 8 factorial. And you can see those 8 factorials can be divided out from numerator and denominator, and you get 10 times 9 over 2 factorial. So there are two ways you can visualize this choose notation. Either it's 10 factorial over 2 factorial times 8 factorial, or you can say, you know what I'm going to do? I'm going to start at 10, and I'm going to go down until I'm I'll go down 2 steps and add 1 back, basically. So I'll go down 10. Let me showcase the idea. I'll go down 10, and I'll go all the way down to 8, but add 1 back. So I'm actually at 9. And then I'll divide by that 2 factorial. Or in other words, if it was something like, let's create something else. Let's say it was 103, choose 15, right? I would go ahead and say, this is the same thing as let's not do 15. That's too much. It's just too much for me to even want to do. Okay. 103, choose 5. I'll start at 103 and start decreasing all the way down, right? Until I get, I'll just keep going here. 99, 98, 97, and so on and so forth. Well, actually what I'm going to do is I'm going to go all the way down to 103 minus 5, which is 98, and I'll add back 1. So in other words, I'm only going to go down to 99 and divide this by 5 factorial. So these expressions, this and 103 factorial over 5 factorial times 103 minus 5 factorial, they're the same expressions. And in general, actually maybe I should put it up here. In general, if you start at k and you choose n, you can reduce that down to either k factorial over n factorial times k minus n factorial, or that can be reduced to k times k minus 1 times k minus 2, all the way down the line until you almost get to k minus n, but you're going to add back 1. And that's all over n factorial. And if you look at that expression, this expression right here, we have already seen. It is this expression right here. It's the expression that is in our our summation, right? This piece right here. So you can also say that this is equal to, let me go ahead and get my pen in here. In fact, maybe I should write it to the right here. This is the same thing as saying 1 plus the summation n equals 1 to infinity of k, choose n, x to the n. And in fact, the choose notation for integers at least is a little bit better to work with, because k choose 0 is defined to be 1. Okay, k choose 0 is actually 1. So if you use this notation and not this notation, then you could say, oh, this is the same thing as the summation n equals 0 to infinity of k choose n, x to the n. Now, the question is, which one should you use? Well, in calculus, to be honest with you, unless you have integers everywhere, I would only use the one that I'm highlighting right now. I'd only use that guy right there, just because you're going to deal with rational exponents, and the other one falls apart if you don't. Okay, or the other one falls apart if you're not using integer exponents. So I would prefer to use that. So let's go ahead and see it in action. Let me scroll over here. And let's go ahead and expand. 2x minus 3 raised to the fourth. Now, to be honest with you, this will have a finite expansion. It'll actually stop expanding after a while. We know that this is only going to go to the fourth power. So, all right, that's not a big deal. But still, I just want to showcase how you could use this. Just remember that we need to get it in the form of 1 plus x to the kth power. 1 plus x to a power, or 1 plus, I should say, an unknown. A lot of people focus in on the letter x. It's just 1 plus something that you don't know, raised to the kth power. So I'm going to slowly get this in that form. I'm going to factor a negative 3 off of both terms. So I get a negative 2x over 3 plus 1. And again, this whole thing is raised to the fourth power. And so that's the same thing as 81, because that's negative 3 to the fourth, times 1 plus negative 2x over 3, again, raised to the fourth power. Now I'm ready to go because that is 1 plus something raised to the kth power. So let's go ahead and see what this expansion looks like. Now let's remember that my version of this, let me go and scroll up to showcase it. My version that I've highlighted here starts at 1 plus, then the summation starts, mainly because it's going to throw people off otherwise. So I'm going to do that. I'm going to say, well, this is the same as the quantity 1 plus, then I will start my summation starting at 1 and going to infinity. Again, the 0th term I've already run. That's just the 1. And it'll be k, which in this case is 4. So 4 times 3 times ... all the way down to the quantity 4 minus n plus 1. So I've just replaced the k's with 4s here. And this is all over n factorial. And it normally would be x, right? Normally I'd say that's x to the n, but it's not x that I'm plugging in. I'm actually plugging in, let me highlight this, a negative 2x over 3. So let me go ahead and write, instead of x, a quantity negative 2x over 3 to the nth power. Okay? And you could, if you really want to, you could distribute that 81. So you could say that's like 81 plus 81 times, and now you can start your expansion, right? So when n is equal to 1, you're going to look at the final number here. When n is 1, you're going to start at 4 and go all the way down until you get to, remember, n is 1, so 4 minus 1 plus 1 is 4. So you're just going to start at 4 and end at 4. Downstairs, it's 1 factorial, and you're multiplying, let me do this, you're multiplying that by a negative 2x over 3 to the first. Plus, now n is going to be 2. So I'm going to go all the way down to 4 minus 2 plus 1, which is 3. So 4 times 3. It's like a factorial in a way, right? Over, now n is 2, so 2 factorial, times negative 2x over 3 squared. Plus, now I know the pattern, right? 4 times 3 times 2 over 3 factorial, negative 2x over 3 cubed, plus 4 times 3 times 2 times 1. I'll actually write that because there's a reason. Over 4 factorial times a negative 2x over 3 to the fourth. Now, we know just from the original function, the original expression, the quantity 2x minus 3 raised to the fourth, that this should be it. We should only end up with an x to the fourth term. But I'm going to showcase that we will actually stop at that, because if you continue, you get 4 times 3 times 2 times 1 times 0 all over 5 factorial times this negative 2x over 3 to the fifth. And actually, each term after that will have a 0. Right? And so it ends up being that the rest of the terms are 0. Plus ... a bunch of zeros at the end. So in reality, what we have is really this expansion. Let me go ahead and say this is equal to 81. And now I'm going to go ahead and clean this up. It won't clean up nicely, by the way. It's not going to be pretty. But at least when I distribute, actually, I'm not going to distribute that 81 yet. I'm going to do it like this. This is going to be negative 8x over 3. And then what do we have? Plus, and so that's a positive 4 and times another 4. That's 16 times 3 is 48 over 2, which is 48 over 2 is 24 over 9. And that's, by the way, times x squared. And 16, I'm just doing the math in my head. I should probably pause while I do that, right? And next one is going to be a negative 64 over 9 times 3 factorial. I'll just write it that way. And let's see. And that would be, by the way, x cubed. And finally, the x to the 4th term. And it's 4 factorial over 4 factorial, so that cancels out beautifully. But we have plus 16 over 81 x to the 4th. Now I'm going to distribute the 81 through. And so we get 81 plus, now actually minus, because that minus sign there. And now we're going to have to do a little bit of calculation. So that's a negative 216x. And let's see, we have 9 times 24, that's 240 minus 20 is 220, 216. Oh, that's nice. Plus 216 x squared minus 96x cubed plus 16 x to the 4th. Just double checking my math here. And that looks about right. So that is the polynomial expansion of 2x minus 3 to the 4th. Obviously something that you could do with algebra very simply, but this is to showcase how the calculus would work. And now we can kind of build this further in another example. I'm going to actually end this now so that you have time to kind of digest the material and remind yourself of the binomial series. And then in the next video, I'll just do a quick example of how you're going to use this for rational exponents.